Um, so we'll be switching gears from the very exciting tutorial earlier this morning on quantum chemistry, and this topic is about quantum complexity theory. But we won't go too far because it's also about physics. It's at the intersection of the two things. Uh, so I'll specifically talking about quantum PCP conjecture, which is in the opinion of many people, one of the most important open questions in quantum complexity. And I'll talk about a progress on that, which is called the NLTS theorem. So the plan is pretty straightforward. Oh, sorry, I should be working here. The plan for me is to give you some background into the concepts that I will need for this tutorial, and then I'll tell you about the NLTS theorem, whose acronym, which expands to low energy trivial states, and then the quantum PCP conjecture. At the same time, as we go along, I have planted lots and lots of, at least 4, as far as I remember, 4 quiz for the audience. So if I feel too on the stage, I might just pick someone to answer that question. So just to make everyone on the same page. But let's see how that goes. So that's my way of well, if for people who know about this area, that's my way of doing probabilistic checkable proof that you're understanding everything that's going on. All right. Well, at the same time, one challenge that I was facing when preparing this tutorial was, well, this audience is pretty diverse. It's not just quantum complexity theory and quantum, Hamiltonian complexity audience here, but many of you were very engaged in quantum chemistry, like me, early this morning. And it's not very clear whether you would right away get the key message if I just went ahead through this tutorial. So let me spend 2 slides giving you a very high-level overview of what I expect as the main message. Even if you don't get much out of what's going on, it's slightly technical tutorial. So even if things don't make sense too much, that's totally fine. These 2 slides are really to kind of get across the big picture. So one thing that I find really nice about many areas of science, and I believe many people also share the same feeling, which is that there are these local simple rules that are sort of serves as the building block of some various areas. Like in molecular biology, you have amino acids, you have, well, also in music, you have musical notes, and you have bricks in architecture and so on. What's very nice about these things is that these local simple rules often lead to very interesting large-scale phenomena, like well, our cell, beautiful musical pieces, and this nice building, which I'm not sure if you saw it or not. If you're too distracted by 7-Eleven here, you may miss out looking up and checking this nice thing out. So that's great. So local rules are simple, we can understand them, and we can use them to build global things. That's really nice. But there's a big problem to this. And the problem is that local rules are also very prone to errors. You start making errors to local rules, and then the whole thing changes. So robustness is needed in any such construction as part of, robustness is needed because local rules can easily be perturbed, okay? So this tutorial, at its from a very broad point of view, is simply about certain local rules that we believe are a good representation of what happens in quantum n-body system. So these, up to very good approximations, these govern how quantum particles interact with each other, okay? And these local rules are quite simple. I'll have a slide on describing everything about them. The quantum PCP conjecture is a search for a very strong form of robustness in these local rules. And that's what makes it a very hard open question. But also it's a very exciting open question because the conjecture has close ties with quantum computation and also with fault tolerance in quantum computation. You can think of quantum PCP conjecture as sort of a fault-tolerant question about these local rules that govern our physical systems. And the NLTS theorem is a form of robustness, not the complete picture, but some evidence of this kind of robustness in these local Hamiltonian systems. Okay, so that's the main thing to keep in mind throughout this tutorial. They know that they know. How do you get to robust way to capture many body physics? Okay, all right. So with that, let me introduce. In fact, let me tell you what the notation that I'll be using, and in fact also maybe introduce to some of you what local Hamiltonians are. So local Hamiltonians, these consist of a collection of particles, these red dots in this picture. Think of them as qubits, and let's say there are n qubits overall. And these particles, they interact locally in some manner. And this local interaction is defined by a Hamiltonian H, which is a sum over these smaller parts. I have put a 1 over m over here for a reason I'll get to in a bit. But this Hamiltonian is composed of these local things. Each H alpha could be one of these yellow circles, and this H alpha is a Hermitian positive semi-definite matrix, things like that. But in a nutshell, it's basically telling you how these three particles are interacting with each other. Okay, and the sum goes from 1 to m or something like that. And the constraint is that each local term acts in an interesting way only on a constant number of qubits. That means this matrix can be any Hermitian matrix on these qubits, and it should act as identity on everything else in the larger Hilbert space. Okay, and also each qubit also participates in a few local terms. So for example, this qubit over here participates in 2 of these yellow circles. This qubit only participates in one circle, and so on. And that's what I mean by locality. Each Hamiltonian term only acts on a few qubits, and each qubit participates in a few local terms. What you see here is a collection of qubits and these circles. This is also called a interaction hypergraph or interaction graph. I'll be using the term interaction graph a lot. And interaction are these local things, and the graph is just telling you, look, that's how I think of these things. Something which is a very reasonable thing to say about these local interactions is that they're all pretty much on the same footing, which means that you don't have a situation where suddenly one interaction is tremendously large in compared to others. And that's a reasonable thing to say, and that's why we have this energy constraint. Each local interaction, it has a 0 eigenvalue and at most an eigenvalue of 1. A 0 eigenvalue basically corresponds to, this interaction term for that quantum state doesn't penalize anything. That's a good thing. And an eigenvalue of 1 basically says that, look, there's too much energy there, which may or may not be a good thing. All right. So with that, just like any Hermitian matrix out there, H is a big Hermitian matrix that lives on these n qubits. So although it's a sum of these simpler parts, in itself it's a giant object of 2 to the n times 2 to the n dimension. So this matrix can, in principle, be diagonalized, and you can find the ground energy of this matrix. And the ground energy is the smallest eigenvalue, and ground states are the states that have the smallest eigenvalue. That's ground energy. It's basically the setup in Garnett's tutorial earlier. Okay, so here is a representation of that. Over here, I've drawn a ground energy here, which is not so red, and higher you go, it's sort of, think of higher energy as sort of more hot system. As you go up here, energy increases, and max energy is at most 1, because the way I chose this Hamiltonian as an average of these local terms. If you don't have m here, then this could go as high as m. But I chose 1 over m here, so this will be at most 1. So one thing that we'll repeatedly come back to in the next 3 hours, so it's really important to maybe ask questions about this, which is the notion of epsilon energy states. So we'll think, so for any quantum state on these n qubits, the energy can be computed by the standard thing people do in quantum mechanics, which is just take the expectation value of the state with the Hamiltonian, and that gives you a number. So that's the energy of any quantum state. Doesn't matter if it's an eigenstate or not. So given that, I'll think about an epsilon, which is a small which will often be a small constant number, like 0.000001 or something like that, or 10 to the minus 6, something like that. And I'll be interested in all the states which have energy at most epsilon, for which this number is at most epsilon. So that forms a small set of all quantum states, and that somehow lives over here. Okay, so that's the notation for local Hamiltonians. Any question? Yes.
Constant number.
Right.
So when you say constant number, do you mean like a fixed number, or do you just mean a small bounded number?
Yeah. So
because
today,
in your diagram, that doesn't seem to be a constant.
Right. You're right. So in this diagram, everything is a constant. Right. No, you're right. So well, think of n as n grows, you think of a family of Hamiltonians for more and more qubits. So this is slightly misleading. You're right. What I should have said here, to be more accurate, is that for each n there is a Hamiltonian. As you think of more qubits, there are more and more Hamiltonians, and for all of them, the local interactions are always something that's independent of n.
Okay.
Asymptotically, as the number of qubits increases. Yeah.
Okay.
So it's sort of a in principle statement.
But there could be some terms with Hamiltonians involving two subsystems, 2 qubits, and some with 3 qubits, and so on.
Yeah, 2, 3, 1, 5.
Okay.
Beyond 10, I won't even go.
Okay.
People start throwing tomatoes at me.
Okay.
Yeah.
Thanks.
Okay. Yes, there's one question over there. So the question is m bounded by a constant? So m will have to scale with n. So each qubit participates in constant number of terms. Each term involves constant number of qubits. So if you just think of just the number of relations, that has to be proportional to n. So m has to be proportional to n as well. Yeah. So m grows. And I might make several mistakes which you will never notice. I'll often call m as n, but I mean, it's not like everyone pays so much attention anyway, even I don't. So, yeah. All right. So is that good?
One more question.
Oh yes. Where is it?
The epsilon energy states, is that within epsilon of the ground energy or epsilon absolute?
Good. Nice. So since people are paying attention, that's nice. So yeah. So this epsilon is within the ground energy. So ground energy could be something and plus epsilon above that. That's what I mean by epsilon energy states. Yeah, you're right. So it should be epsilon plus ground energy. Yeah, thanks. That's a very good point. Okay. All right. So having said that, this is again the same picture that I had before. This slide is going to introduce a slightly strange notion. It's a technical point which you can keep in mind if you like. Otherwise, you treat it as a neutrino, just pass by your brains. So this is exactly what I said earlier about epsilon energy states. There is a notion of error, which is the set of states, quantum states, that you can obtain from the ground state by applying some error to some qubits, like applying some unitary to some qubits. So start with the ground state, apply some unitary that acts only on epsilon times n qubits, and that gives you a new quantum state. That quantum state I'll treat as an epsilon error state. The way to think about it is that it sort of makes you make an error on purpose on a small set of qubits. The quantum state psi looks exactly like phi everywhere else except those epsilon n qubits. Okay? So this notion makes a lot of sense in the theory of quantum error correction, well, because errors happen on a few qubits and then you want to correct them. But here we'll kind of treat them more generally for good reasons, to understand the key insights that go in this tutorial. So since this is a slightly new notion, so here's a little quiz, the first quiz for people here, which is, well, the two questions here. First, is every epsilon error state also an epsilon energy state? And second question is every epsilon energy state also an epsilon error state? So you have 2 minutes to answer this. Do you already have an answer? Let's wait for a few more seconds, and then I'll get back to you. Yeah, I'll ask you first. All right. So yeah, go ahead. I mean, do you want to give the answer?
I guess yeah, because epsilon air means that you're epsilon away from the ground state, so that's true.
Okay, that's the first answer.
Yeah.
Okay. Any more thoughts about either of the two questions? Yeah. So yeah. Any.
I'd say not quite, but close.
Okay.
Because since you only act on epsilon n qubits, then perturbing by u will only perturb some small number of these H alphas, and it's going to be that number of H alphas is going to be given by how many of the local terms act on these few qubits that u perturbs.
Okay. And how about the second question?
I don't think so.
Okay, you don't think this other way is true. All right, so any more attempts at it? All right, so indeed, so the first answer pretty much both were quite there. So the right version is as follows. Sorry. Oh yeah, I didn't do it very well. So every every epsilon error state is also an order epsilon energy state. What this means is that since you're only perturbing epsilon n qubits, and each qubit participates in at most some constant times epsilon constant number of terms, you will only ever violate at most constant times epsilon n terms, or you'll only ever create at most constant times epsilon energy. So the energy will be not exactly epsilon, but of the order of epsilon, roughly. Yes.
Why you define it like the epsilon energy state? Do you mean like not instead of the set of state with energy smaller than epsilon? Do you mean with energy higher than ground state by epsilon?
Yes, yeah, that's right.
Oh,
It's energy higher than ground state by epsilon.
Okay,
Sorry,
sorry,
I should have been
sorry.
more careful earlier.
Okay, yeah, good.
Yeah.
That makes sense.
Yeah, great, thanks. Right. So, but on the other hand, if you have an epsilon energy state, it's not clear why that's a low energy state was obtained from a ground state by making a small change. You might have made a global change, a weird change all over the place, and then made it. And this distinction is not just a distinction of definition, it's a very subtle point that will keep showing up in this tutorial. So I just thought to put it early on, all right? So indeed, every epsilon error state is also an order epsilon energy state, and every epsilon energy state need not be an epsilon error state. So the notion of energy is stronger than the notion of error, all right? And in fact, yeah, we'll see how this difference really plays a key role and sort of was the main obstruction in one of the questions that I'll talk about. All right, so that's fine, but let me give some examples of local Hamiltonians to get people who may be a little bit lost on the same page, which is, well, here are 3 examples that I'll take. First example is a Hamiltonian which is a sum of these terms. It's a Heisenberg model where, I goes from 1 to n for the qubits, and qubit I and I+1 interact as xx, yy, zz. So this interaction is acting as a spin chain. You can think of qubits arranged on a line, and the neighbors are interacting. So this notion is not just notion of locality, it's also the notion of geometric locality. There's a geometry there, a low-dimensional world in which this system is living, and that world not only is each qubit interacting with constant number of qubits and each constant number of terms and vice versa, but also they have a structure that comes from our real world that we see in day-to-day life. So that's a geometric locality notion. But at the same time, you can have a different kind of thing where for example, you have a graph. There are n qubits on the vertices, and as I mentioned, there's an interaction graph where qubit I interacts with some qubit j via the same xx, yy, zz interaction. This is still a local Hamiltonian for today, but it's not a geometric local Hamiltonian. So many graphs cannot be put inside 2 or 3 dimension without creating long-range interaction. So if you have a graph in general, you can't just embed this in 2D or 3D or 4D with by keeping locality. So that makes a difference between geometric locality and locality. And the last example of a Hamiltonian is, sorry, is what one can call a code Hamiltonian. And this will show up as well later. This Hamiltonian doesn't seem very physical like the Heisenberg model, which has been around for 100 years. People have studied so well, and Heisenberg model is a good representation of what happens in magnetic systems. This Hamiltonian feels a bit weird, but it's very useful. And this Hamiltonian is a sum of x and z things. So just a quick note about this. Sorry, one sec. Yes. So in this notation, x to the a basically means that if a is an n-bit string, then x to the a is a shorthand for a poly x at all places where a is equal to 1. So if a is like 1, 0, 0, 0, 0, then x to the a is basically x at qubit 1 and 0 and identity everywhere else. So this code Hamiltonian is defined from the stabilizers of a quantum code, of a quantum error correcting CSS code. And it consists of the x stabilizers and the z stabilizers. The x stabilizers come from the parity check matrix of the x part of the code, and the z stabilizers come from the zth part. And to make sure that x and z commute, the condition that px and pz should have orthogonal rows is imposed. So this if you have seen quantum error correcting codes in the past, you can define a CSS code from there. Yeah, unfortunately, I will not cover quantum error correction in this tutorial, but you can ask questions if there's some confusion over here. Okay. And yeah, and the code that we're thinking about is basically an NKD code, where k is the number of encoded qubits, and that shows up in the normalization here. Yes. So it's local if the parity check matrix is low density. Yeah, otherwise not. Yeah, good question. Sorry. Okay. All right. All right. So that's all about quantum computation. As I mentioned, sorry, that's all about local Hamiltonians. As I mentioned, we'll also discuss quantum computation a lot today. So let me tell you a little bit about quantum computation, at least what I need in this tutorial. So I'll be focusing on the circuit model of quantum computation, in which you start with some qubits, which are in blue here, and you apply either 1 or 2 qubit gates to the qubits. Now, size is the number of, for me, is the number of gates that you apply in the system, and depth is the number of layers of gates. So sometimes you may want to parallelize your computation and apply many gates in one layer. So you may ask, how many layers do you need to really go ahead and do all that? So often in real world, we can only apply circuits on an architecture that lives in a on a chip or something like that. But today I won't make any such assumption, and I'll assume that all the gates, they follow all-to-all connectivity, which means that at each layer, gates can act on any pair of qubits as long as the gates don't interfere with each other, as long as there is no overlap between the two gates. All right? So that's the model I'll assume. And that's called all-to-all connectivity. Sorry. I had a pretty spicy food earlier. Apologies for that. So once you have a notion of a circuit, a very useful notion from that is the notion of light cone. So imagine any qubit in the output over here. And you may ask, well, how many qubits from the input influence that qubit? And to really figure that out, you have to trace back all the gates that acted on the qubit in the previous layer, and so on and so on and so forth. So when you do that, what you get is a light cone that emerges from the output qubit. And that's what's shown over here, where these gates are all the gates that eventually influence this qubit, but these gates over here don't influence. In a very precise sense, if you had to set all these light-colored gates to identity, if you switch them off, the quantum state on this qubit would stay unchanged. It would be the same as before. So this notion is very operational as well. It's not just a definition. So notice that because I'm allowing all-to-all connectivity, each time as you go up in the layer, the number of, although it's not clear over here in this picture, but it turns out that at each depth, the number of influential gates increases by a constant factor. So what happens is that the light cone of any output qubit is at most exponential in the depth, but can be as large as that. Of course, if you restrict your gate to a 2D or a 1D or a 3D architecture, then you have polynomial in depth as the size of light cone. But here it's exponential. Okay? All right. So the thing that shows on the top, the input qubit, is pretty relevant for us too. So usually when you think of quantum computation, we like Shor's algorithm, we start with something very simple like an all zero string. We initialize the qubit in a very simple state, and we apply our gates. So often when you think of quantum computation and solving problems using quantum algorithms, we are often interested in input that is 0 tensor n. But there's a whole area of interesting quantum computation that doesn't really start there. That quantum computation starts from some zeros, but also something maybe in the beginning, there could be something more complicated, a weird quantum state in the beginning. And that's the problem of quantum verification. Like, sometimes you may want help from some very powerful quantum person with a lot of money and so on, and the power to create weird quantum states to help you solve a problem. So in that case, you're in the world of QMA, and you start with this kind of quantum state. So just more specifically, a QMA is a class of problems that you want to solve, for which in the yes case, I mean, the answer is always yes or no. In the yes case, you can provide a quantum state. Someone can provide you a quantum state, using which the quantum computation eventually says, good, the answer is yes. In fact, that happens with high probability. And in the no case, for any quantum state, the quantum computation rejects outputs no with very high probability. And BQP is basically when you don't have this thing, you just start with all zeros and figure out yes or no answer. So here is an example of, yeah. So here's an example of a problem in QMA. You're given a local Hamiltonian as before. You want to figure out, is the ground energy very close to 0 or it's a large number. So, sorry. So to really figure that answer out, you may have to, do some crazy computation. You may have to diagonalize the whole Hamiltonian and then, try to find out the smallest eigenvalue. That can be very complicated. But if you had the access to someone who can prepare ground states, then you could ask that person to send you the ground state, and you could measure the energy. And hopefully energy is 0, or maybe it's large. So in that case, you're asking help from someone, but you don't trust that person that much, and you're trying to estimate the energy using that help. So that's where the quantum state that's not 0 comes in handy. But of course, that's sort of an idealistic scenario because, well, who has the ability to construct these complicated ground states? We don't know. Maybe nature can do it for you. But on a more realistic setting, of course, more practical settings, you want to just start from scratch, start from all zeros. So a very example of a problem in BQB is the famous factoring problem, indeed, that we all love. All right. So in this tutorial, the distinction between QMA and BQB is not so important. Of course, it's a very important distinction when one starts to think seriously about these things. But we'll just think of both as quantum computation. Or if you know about these things, then just as quantum verification, or whichever, that's fine. But I'll just be calling them as quantum computation as a whole without specifying which and which. Okay, so any questions so far? All right, I'm assuming you're paying attention because the next quiz is coming soon. All right, so now we have this world of local Hamiltonians. We have the world of quantum computation. You might have noticed something similar to both, which is they both run by local rules. For local Hamiltonians, the local rules are basically these local interactions. For quantum computation, local rules are these gates that kind of work, that make things happen. So, one might just wonder, two things look similar superficially, okay, I shouldn't give many examples. I was thinking AI and quantum mechanics or something like that. But people come up with crazy ideas about how to connect two things that superficially look mysterious. But today, we're trying to do something more serious. So the claim is that local Hamiltonians and quantum computation are very closely connected, okay? And that connection, in fact, goes both ways. But today, specifically, we'll need that connection in one direction, which is that given any quantum computation, you can write down a local Hamiltonian that carries the answer to the quantum computation. Okay? And that's the very famous quantum Cook-Levin theorem that was shown by Kitaev using ideas from Feynman's paper on quantum computing, maybe the only paper of first paper. So the statement is that given every quantum computation of the form that I described earlier, whether QMA or BQP, of certain size m, having m gates, you can map it efficiently to a local Hamiltonian H, which I'll give a subscript Fk for Feynman-Kitaev, with very interesting properties. First property is that if the quantum computation accepts, and accept means good, the answer is yes, there is a factor, something like that, then the ground energy of this HFK is very, very close to 0, exponentially close to 0. Okay? And if the quantum computation rejects, more precisely for QMA, it has to reject for all witnesses, but I'll skip those subtleties here. Then the ground energy of this Hamiltonian is 1 over m cubed. So there's a difference between ground energy based on whether quantum computation accepts or rejects. All right? So this mapping is known as the quantum Cook-Levin theorem. And here's a even more interesting thing about this mapping, not just the fact that it encodes this answer, but the very interesting thing is that this mapping not just encodes the answer, it encodes the whole quantum computation. So you can write this H Feynman-Kitaev, which I haven't really described to you how it's constructed, so apologies for that. I won't be doing that actually today. But it turns out you can write it into 2 parts. One part which is famously called H clock, because it keeps track of time of how computation is progressing. And one is H out. It just wants to see a yes answer, an accept answer, that's all. So H clock has the property that it encodes the quantum computation, as you can see here. So here's a quantum state that's known as the history state, which was defined by Kitaev. It basically, for every time, it encodes a partial computation of that quantum computation you're thinking about. And when small t becomes m, the whole computation is laid out in front of you, and you can read the answer. You check, is t equals m? If it is m, then you just go ahead and measure the output qubit. So the whole computation is laid out in front of you at t equals m. But of course, you have to measure a couple of times to get t equals m. That's fine. So H out simply prefers yes on the output qubit. That's all it really wants. But it's nothing very surprising about that. All right. So what you saw in these 2 slides is that, well, there is a way to go from every quantum computation to a local Hamiltonian. Not only in the sense that the ground energy encodes the answer to the computation, but at the same time, the ground state also encodes the computation itself, which is a pretty surprising phenomenon. And it's sort of and there's a classical version of this, which is known as the Cook-Levin theorem, and that's the basis of the theory of NP completeness. So it's a pretty useful notion to have. So with that in mind, now it's the time to introduce the quantum PCP conjecture to you. Quantum PCP conjecture is asking an even stronger statement than what I said earlier about quantum Cook-Levin theorem. It's asking that is the following true, that for every quantum computation, you can write down a local Hamiltonian H, such that if quantum computation accepts, then the ground energy of H is close to 0, like very close to 0 probably. And if the quantum computation rejects, then the ground energy is very, very large. It's roughly a constant. And keep in mind, the way I'm defining energy is an extensive notion. Like I divided by m many slides ago. So in the usual notion that maybe Garnett was covering earlier, you should read this as theta m, like energy as large as the number of qubits. But of course, I normalized it divided by m for convenience here. So that's the scale you are expecting. You're expecting the energy answer to be stored at extensive scale. Whereas in the Feynman-Kitaev case, the energy is really, really small. Yeah, it's roughly 1 over m cubed. It goes to 0 as m increases. And here we want something much stronger. Sorry, it's a bit slow. So the answer to quantum computation can be obtained by estimating the ground energy of a local Hamiltonian up to constant precision. And that's what this conjecture is asking. So on the face of it, this sounds like a good question, okay? It seems like a hard question and people have tried for a long time. But you might also feel, well, sure, but I mean, even if it doesn't happen, what's the big deal? And also, if it happens, then what's the big deal? What's the impact on what we know about nature and so on? So here's my attempt to kind of convey that this is a pretty useful statement also for physicists, which is not clear from this itself. I mean, it seems more like something we're asking about quantum computation and taking help from a physical system. That's great. But is there a other direction as well? Like, if this statement is true, what kind of impact would it have on our understanding of how physics works? So here's an attempt at that. And for that, I will need a slightly speculative, but also it's a stronger, but I think a reasonable version of this of this conjecture, which is that, well, similar to what happens in H clock in the Feynman-Kitaev case, let's postulate that every quantum computation can be mapped to a local Hamiltonian such that all sufficiently small constant energy states, in fact, encode the quantum computation. Not just the answer, but also the quantum computation. Let's say that happens, and you can read off the answer from certain qubit. So this is quite analogous to what happens for clock Hamiltonian. The ground state encodes the quantum computation. And here we're asking, what if all the low energy states encode the quantum computation? Yes? What does it mean to encode the computation? So I don't know, because that would be the answer to this conjecture, of course. But maybe something similar to what you see here, over here in this slide. The ground state encodes the quantum computation in a very specific form here. And what I'm asking is that all the low energy states encode the quantum computation in certain form. That doesn't have to look like this, but it looks like something. Yes? What does it look like in the classical case? In the classical case, that's a great question. In the classical PCP theorem, it's a crazy encoding, which I haven't tried to venture into too much for good reasons. But it's sort of a variation on the Cook-Levin tableau, if you have seen that. It's basically all the bit strings are laid out in front of you, and you just check for consistency that the gates were applied properly. Yes?
So it seems like it's not like you can use the state to do the computation again or something like this. It's just like the state depends. It's just like the state depends a lot on the computation, but it's not like an encoding of it that you can use it as a program or something like that.
Oh, so you just read the answer. The state already. So for example, you can ask the same question for the Feynman-Kitaev ground state. You don't run it anymore. You just measure the qubit and you get the answer. So as in the state already encodes the computation and you just have to read it. That's all. As in, you don't need to do any more computation any further. Just do a measurement and that's it. You get the answer out.
Do you mean it encodes the output or like?
Yeah.
Not the computation?
Well, I mean,
okay.
Well, oh wait, what's happening here? Sorry. Well, as far as I'm concerned, in that expression, it pretty much encodes the gates. I mean, I could potentially read out the gates out of the computation as well. Yeah, nice. It includes the amplitude as well. But it's encoded as a quantum state. Yeah. All right. Okay, so thanks for that. So, well, here's the reason why I'm alluding to this slightly stronger notion, which I expect should be true, is because, well, sorry, one more point is that, well, how does that go from this stronger version to the original version? Well, just put a H out on the output qubit, and the energy is 0 if answer is satisfied by H out and one otherwise, high otherwise. So here's a way to think about why this is useful. That's because, well, we know that quantum computation is powerful enough to simulate lots and lots of physical systems. So for example, if you want to prepare Tory code ground states to witness topological order, if you want to simulate a Hamiltonian evolution or so on. So we know that quantum computation as is, it has the potential to really simulate lots of interesting physical phenomena. Of course, we don't know how to build one yet, but that's a different point. So let's say you discovered a new physical phenomena in your lab, and you measured some local expectation values, and you found some exotic pattern which was not present at high temperature, something very specific about ground state, and you discovered something very interesting that happens at very low temperature. And then that's good, but then you're wondering, well, is it possible that this phenomena also occurs at higher energies, like in the Gibbs state or something like that? So if you could just, in principle, of course not in practice most likely, in principle, you could use the encoding that's could exist from the quantum PCP. And that encoding, from there, you could read out the same exotic pattern, not just in the ground state, but all low energy states. In fact, all constant energy states. So I'm not saying that this should be used as a way to get to high temperature superconductors or something like that. That's a bit too much to claim, of course. I mean, and I'm not expecting you all to throw more tomatoes at me. But you know, I mean, at least as a matter of principle, this is a way to get to observe interesting low energy phenomena at higher energies, at least in principle. So you could use this as a tool to do that. Okay, all right. Yes. Right, so the quantum computation would be basically coming from here. So first verify that you have the ground state of this Hamiltonian that you prepared in the lab, and then measure this physical observables and accept. So basically it's a QMA protocol. You first run the, verify the energy, no ground, if it's high energy, reject, ground energy, accept. And then after that, measure the local expectation value. And if you see that you observe the pattern that's exotic, accept, otherwise reject. So that quantum computation can be encoded into via this PCP thing. Yeah, I kind of swept that under the rug. So you would, basically the ground energy would be, low energy states would be all the accepting configurations of the original computation, and they would exhibit the same behavior at higher energies.
Okay, I think I understand.
Yeah, that's a question.
So is another way to look at it is to say if once I accept it, I want to know some other properties of the state. Is it related to asking like, okay, once I know that I can accept it, like, can I say something else about the state as well? Say like in terms of like condensed matter properties, like correlation lengths or etc. something like that.
I see. So do you observe those things at maybe? Yeah.
So my specific question is, once you know the answer is yes, like can you know more about the ground state?
I see.
Say if there is a product state nearby, so maybe you can't know more because your product state can be given as your verification. But say if you want to know more, you actually need the state, right?
Right. So all I'm saying here is that, well, so it's not about testing the state itself. It's more about testing a specific expectation value. But maybe I misunderstood. We can talk later about this question. Yeah. All right. Yes. Some in the back.
Yeah, for this Feynman-Kitaev encoding, I just couldn't see how you can recover the computation from the ground state. Because what I understand from recovering the computation is that you want to know, by looking at the ground state, what the unitary U1 was and what the unitary U2 was, going right up to the unitary UN. And I didn't quite see how you could do that. Could you tell us how you do that?
That's a good question. So when I said encoding, I didn't mean to be able to recover it. So I didn't care about that in this context. I just cared about encoding the computation and getting the answer right. But that's a good question itself. Like, can you recover it? And one way to do it would be to, if you had the power to precisely learn the local marginals of this state, you could try to learn the Hamiltonian itself, H clock. But I don't know anything beyond that. I don't know if that would totally work in practice or not.
Yeah, I see. So you're not talking about recovering the individual unitaries in the computation.
Yeah.
You're talking about something else.
I just want encoding. Encoding in a manner that you can indeed measure the answers. You can get the answer right.
Okay, thanks.
Yeah. All right. So seems like a very open-minded audience. I mean, I was thinking people would be, burning me alive for trying to make connections to physics, but that didn't happen. So that's very nice. But it's great that that there are no objections to this yet. But there's another objection here. Go ahead.
Oh, I just wanted to ask a clarification question.
Yeah.
So what you're saying is, if quantum PCP is true, so like I have a Hamiltonian exhibits, let's say, superconductivity. Even if I can't synthesize a material in the lab, I can mathematically construct a Hamiltonian that would exhibit high TC superconductivity.
So when I was preparing these slides, I was kind of I wanted to say something like that, but I don't know anything at all about superconductivity. But maybe. I mean, I shouldn't say it so out loud, such a statement. But you know what? I get you. basically. Yeah. But again, I don't understand enough about superconductivity to really say if that matters here at all. But why not? All right. So yeah, sorry, this is a bit slow here. All right. But here's a big catch about all this, which is that, well, even if this quantum PCP Hamiltonian exists, how does it look like? Where does it live? Does it live in our 3-dimensional world, 4-dimensional world? Like, could it be realistic at all? So that's where we are at our quiz 2 or 3, I guess. I don't remember anymore. And the quiz is as follows, which is, well, which of the following Hamiltonians look complex enough to you that you expect the ground or low energy states would encode something as crazy as a quantum computation? So again, you have 2 minutes to get an answer. So options are Heisenberg antiferromagnet in 2D, 3D quantum recurrent encodes, and AKLD model in 4D. Yes. Yeah. Yeah, exactly. 2D lattice, 3D lattice, 4D lattice. Yeah. So D stands for lattice dimension. Yes. Yeah, sure.
I just want to confirm the mapping that you said for the quantum PCP theorem. So it's for every circuit plus input, right? So every circuit plus input is mapped to a Hamiltonian?
So input, so in the case of BQP, input is all zeros. So that's just fixed, so there's nothing to map there. For QMA, input could be an arbitrary quantum state. Mapping isn't a part of it. Mapping is sort of independent of the input witness. Because input can be very complex, but mapping is efficient. So mapping is in a manner that if there is an input that gives the right answer, yes, it gives the answer yes, then the ground energy is 0. If there's no input that gives the answer, then ground energy is plus.
Sorry, why is the input all zeros for BQ? We run a circuit on an input and get the answer?
So you start with all zeros and then run a quantum computation for BQP.
Okay.
Yeah.
Thank you.
Sorry, so any ideas about these questions? Which one do you think looks complex enough to you that you would think it can encode something as complicated as a quantum computation? 4D. Okay, great. Okay, how about 3D? Okay, possible. All right. Okay. Any more thoughts over here? Heisenberg? Okay. I almost feel like you know the answer over here, but fine. So look, the answer is surprisingly none of them. Yeah. Yeah, so I mean, given the confidence from that side, I was almost sure they knew that the answer is none. So here's a very interesting phenomena, which is going to be very relevant for us in the second part of this tutorial, which is that no local Hamiltonian that lives in a small dimensional world, a small dimensional lattice, is capable of being a quantum PCP Hamiltonian. And here's the reason for that. Of course, assuming that quantum computation is really complex, which we believe all of us do here. So low dimensional Hamiltonians can't be quantum PCP candidates. And the reason is that for every Hamiltonian that lives in low dimension, and for any epsilon, a constant epsilon you give me, there is a product quantum state. It's not like single qubit product state, but it's a product state on a constant sized qubits that achieves that low energy. So this always exists. And the way you do it is simply you cut the lattice into these parts, where you cut this lattice into squares of linear dimension, roughly 1 over epsilon or 2 over epsilon or something like that. So when you do that, here's what happens. You ask, well, how many local interactions are these red lines really crossing? So of course, they're not crossing anything that's within each square, but they're crossing things on the boundary. And it's a very simple calculation to check that they're only crossing epsilon fraction of local terms, as see over here. So what you do is that you simply choose the ground state on each local square, which satisfies everything inside the square, but can potentially create a lot of energy on the red lines. But there are not enough red lines out there to capture enough Hamiltonians. So for every epsilon, you see that you can get an epsilon energy state. And this is this product states are too classical to encode quantum computation. And I'm assuming that people here come with the mindset that quantum computation is maybe something which cannot be captured classically. That's what I'm assuming, but maybe I'm wrong. But that's what this is saying. So in a low dimensional lattice, this is always possible, and you are not able to capture the power you expect for encoding quantum computation. So product states there's always a product state in the low energy of low dimensional Hamiltonian for any epsilon. So to avoid this, what you need is that these red lines should not cut a small fraction of these interactions. They should be cutting lots and lots of interactions. And for that, what you need is that the interaction graph, the graph that connects these qubits, should not be living in a low dimension. It should be living in some very high dimensional world. And the right notion to capture that requirement is known as expansion. It basically says that if you, for typical line, for any cut that you make, any large cut that you make in a high dimension graph, you end up cutting a large fraction of terms. Yes.
Whenever you say low dimensional, do you mean constant, or can it also be like log something?
So for this context, I think log. I think log might be fine too. Yeah, I'll have to double check.
Okay, thanks.
But log will be definitely fine. Yeah. All right. Okay. So well, the summary so far is as follows. I think we are pretty much right on time. I'll just say a couple more slides for the next one, then we can take a break. So the summary is as follows: that quantum PCP conjecture seeks a robust encoding of quantum computation in local Hamiltonians, and very specifically in all low energy states. That's what we're looking for. It's a very tough question. And in fact, I just pointed out just now, it's a difficult question also because such a Hamiltonian is not really physical. It should live in a high dimension, some world which we don't really experience in day-to-day basis. But just a quick point here is that, well, people are able to engineer long-range interactions these days. So maybe these systems could be engineered if we ever come up with one. And the one important point is that the conjecture is wide open, but we have made progress on the weaker statements, and that's what we'll see in the next section. Also, the structure of quantum PCP Hamiltonians is getting clearer. So we know, for example, it should live in a high-dimensional interaction graph, whatever that means. I will not be giving a formal definition of this high-dimensional graph throughout, but you'll get a sense of it, I hope, as we go along, because the definition is slightly technical. Yeah, so that's the content of the first part of the talk. All right. So next I'll talk about the low energy trivial states theorem, and the theorem that was proven recently by with Nicholas Brookman and Chinmay Nitke is as follows: that there is a universal constant epsilon and a family of local Hamiltonians, exactly the way we have been talking about so far, such that for all these n, think of n as the number of qubits, and all epsilon energy states that doesn't depend on n. Epsilon is some universal constant, a very tiny number. The quantum circuit depth to prepare the quantum state psi n is at least log n. So this conjecture is saying that there is a family of Hamiltonians out there for which all low energy states require at least log n depth of quantum circuit to prepare. Okay, so I threw it at you, this statement. Our goal is to understand the statement and understand its connection to quantum PCP conjecture, and also understand why circuit depth is important at the same, and also why log n, from where this log n comes. So we'll try to understand all aspects of this statement in this section. So this question, just a bit of background, this question was posed by Friedman and Hastings in 2012 as a necessary consequence of quantum PCP conjecture. I'll explain why. And the Hamiltonian family is actually the code Hamiltonian that I showed you earlier, of a very specific kind, which is now called a good quantum LDPC code that comes from some breakthroughs that happened 2 years back, specifically by Panteleev and Kalachev. And as I mentioned, the goal is to understand what ingredients of the code really lead to this property. All right. So the main claim here is that requiring log n quantum circuit depth to prepare a quantum state should be viewed as a signature of something complex, something hard. That's not always the right intuition, but sort of feels a bit necessary. So a few slides about what do you mean by the signatures of hardness. So circuit depth plays an important role in sort of classifying which quantum states are simple. Oh yeah, go ahead. Yes. As I defined depth earlier, it's the number of layers you need to.
But what maybe I missed in the beginning, but what is exactly a layer? Because that may vary depending on the field.
Oh, so if you want to run a quantum circuit and you're allowed to parallelize it as much as possible, like all the gates that don't interfere, you can apply in one layer. That's what I mean by layer.
Okay, thank you.
So a state that's generated by a constant depth circuit is simple. It's not hard. So for example, all zero states is a pretty simple quantum state, and I claim that any state that's prepared by a constant depth circuit is also simple. And not simple is what we're calling hard. So let's go back to this picture that we had earlier. Here's the quantum circuit, and it's at a certain depth. And let's think of operator O that acts on this small number of qubits. The operator O could be a local Hamiltonian term. It could be something else like magnetization, whatever you like. That's choose your favorite. That's an operator. The claim is, as I mentioned earlier, to compute the expectation value of this quantum state with this operator, you only need to care about the qubits in input that influence these 2 qubits in output. And that's exactly what light cone captures, as alluded to earlier. So for one thing, this quantum state, if it has T layers only, you don't need so many parameters to describe it. You need roughly n times exponential to the T parameters to describe, because you don't have so many layers. Each layer has some number of gates, and there are like order n gates or something like that, and you do it for T steps. So it should be order n times T, but turns out it's order n times e to the T for reasons you can ask me later. So that's one thing. So to describe a state generated by a low depth circuit, don't describe the amplitudes of the state. Describe the gates that went into writing down this circuit. Sorry, and that doesn't need so many parameters. That's one thing. Second thing is that, as I mentioned, that to compute any expectation value with this state, you don't really need that much computation time. You only need to keep track of all the input qubits that will ever influence this output qubit. And there are only exponentially in T many input qubits. So the Hilbert space dimension is doubly exponential in T. So as long as T is smaller than log n, this is a polynomial time computation. So especially when T is constant, this is all linear time. And that's what and that's sort of the reason why you might have seen VQEs, QAOAs that run at constant depth. People like them because it's easy to compute expectation value with those objects. And that's basically the intuition. It's the light cone argument, pretty much. That the light cone is not too large, so you're fine. Yes? So T is the depth. Yeah? Yes. And time is the time it takes to classically compute expectation values.
Oh, I see.
Someone tells you, here's a list of gates that I'm going to apply on this all zero, and that's my quantum state. You want to compute local expectation value. That takes this much time. So in particular, to compute the energy of any state that's prepared by a constant depth quantum circuit, you only need linear time, okay? Or polynomial time if you're interested in log circuit depth. So that brings us to the third quiz to make sure we all understand the notion. Before third quiz, I'll just answer this question here. Yes?
Could you go back to the previous slide, please?
Oh yeah, sure.
So the first statement, any n-qubit state generated by depth t can be described by order n parameters. It doesn't hold for depth 0.
Why? It's e to the 0 is 1, so it's order n.
But you cannot describe n-qubit state by n parameters.
Just describe the gates. So write down the gates. Like if depth is, yeah, but start with all zeros, sorry. You start with all zeros.
Okay.
Sorry.
It's not any n-qubit then.
Yeah, start with all zeros here, acting on all zero.
Okay.
Yeah.
Thank you.
Yeah, I almost had a heart attack there, but I'm glad it worked out. So the quiz is that which of these 3 quantum states can be generated by a constant depth quantum circuit? So again, I won't bother you too much with quizzes, but this is probably one of the last ones. So let's just deal with it for now, because it's an important notion to keep in mind. You can answer both. But it's a ground state in sector of Hamming weight sector 1 only. It's not a unique ground state, I think. As in, if you don't restrict the Hamming weight, it might be maybe of a gapless Hamiltonian. Right. But don't you need to restrict to only one Hamming weight or something? I don't know, but we'll talk about it. All right, so any claims for what's, well, who do you think the first one requires a constant circuit depth? I mean, yeah, there we go, awesome. I'm maybe proud, not of myself for this question. Second one, what do you think about second one? What's second one, can it be prepared by a constant depth circuit? Yes, okay. I know you're playing with me, fine. Anyway, anyone else? You don't think so? Okay, all right. And third one, do you think third one can be prepared a constant depth circuit? Yes, okay. Sorry? For unary encoding, I see. Okay, that's new to me as well, I'll ask you later. Yeah. But you have to control, make a control, right? No, on the first.
It's a passive rotation.
Okay, I'll have to ask you more about that. The ladder, yeah, exactly. So that would be depth time. Yeah. So All right, so there's some discussion going on here that's not super relevant for us to, right now. The key point is that, look, the first, you would intuitively understand that indeed the first state is a plus state of n qubits. Yes, it can be generated by depth 1 circuit. That makes sense. Second case, you feel it in the bones that, yeah, a cat state with all zeros and all ones is a long-range entangled state. All the qubits are entangled in a weird way. That should not be generated by a low-depth circuit. Third one as well feels slightly entangled. But what's the reason for that? Why that really holds as a proof, as a mathematical statement? So we'll be thinking about that quite a bit in the coming slides. But and it turns out that indeed the second and third can't be generated by constant depth circuit, even approximately, as far as I know. But we'll understand that in a bit as to how do you really capture that in a mathematical manner. So before I do that, let me just mention that there are also other ways to capture hardness, not just by circuit depth. If a state is a stabilizer state, that's also simple because you can describe it easily using stabilizers. You can also do expectation value computations easily. So if a state is close to being a stabilizer, you can think of it as a simple state. Far from it, you may want to call it a complex state, but it's not super clear. And it turns out that, well, there are these various notions of trying to capture complexity in a quantum state, which could be via circuit depth, via how far away you are from being a stabilizer state, and so on, by quantifying things like magic or something like that. But the classes that I talked about earlier, QMA and BQP, there is a way to capture those notions succinctly by the assumption that QMA is not equal to the classical version of QMA, that's NP, or BQP is not equal to classical computation, BPP. This is a way to formalize our intuition that quantum computation cannot be captured by classical means in general. Of course, for specific states like plus state, of course, you can capture everything classically, but for most general and useful tasks, you don't expect to do that. So with that, let me give you the connection between quantum PCP conjecture and NLTS conjecture. It turns out that the NLTS conjecture, as observed by Friedman and Hastings, is a necessary consequence of quantum PCP conjecture and the assumption that quantum computation is somehow more powerful than classical computation, which is QMA is not equal to NP. So the way to think about it is that, well, if QMA is not equal to NP, then there should not be any classical way to verify that you have ground energy or not. You are in the ground energy 0 or not. So, and quantum PCP conjecture says that it's hard, it's QMA hard, to estimate the ground energy up to constant precision. So if there was any low energy state that could be represented using a shallow quantum circuit, a constant depth quantum circuit, then that would be a problem for us. Because as we discussed earlier, a description of a low energy state, or a description of any quantum state in terms of a constant depth quantum circuit would allow you to compute energies efficiently. So all you need is a classical verification procedure to estimate the energy. And that, we are assuming, is not possible via QMA not equals NP. So no low energy state can be efficiently described by an ansatz which allows easy computation, including constant depth circuits or even stabilizer states. That's what we are looking for ideally. But this conjecture was specifically about constant depth circuit with other phenomena like topological order and stuff in mind. So basically, the way to think about this is that we know that if quantum PCP conjecture is true, then NLTS would, for all purposes, be true. And the source of hardness, the reason why you're getting a high circuit depth, think of that as something like not being simple, being complex, or being hard. That source is coming from this assumption that QMA not equals NP. But this conjecture itself is not asking that, because we don't have a proof of quantum PCP conjecture. This conjecture is asking, is there any other source of hardness that you can identify about local Hamiltonians, which forces high circuit depth at low energies? And that source of hardness is what we're trying to understand in the coming slides. That's sort of the proof of this conjecture. All right, so let me see, how much time do I have? I was thinking of taking a, so is it okay if I take an early break or no? Sure, so let's just take an early break. We'll come back in 30 minutes? Yeah, I mean, either's fine. I just want to take a break here because we'll switch now to quantum codes.